not in slideshow.
Yeah, you can put it in the full screen mode, Jinmya.
Yes. Is that
Yeah,
okay?
yeah, this is good.
Yeah.
Yeah, it's okay.
Okay.
Thank you, Jimmy.
So please go ahead.
Yeah, thank you, Jimmy. Sorry for delay. Today I'm gonna have an overview of the disease resilient and energy efficient centralized air conditioning systems before the other speakers enter to following topics. Can I have the next slide, Jimmy?
Okay.
First of all, a brief introduction to building energy efficiency. Then we're going to discuss energy efficiency strategies. How should we reach this target of the better energy efficiency, better performance of the buildings, and disease resilience of the central air conditioning systems relevant. And last, a short summary at the end. Next slide, please. So as everyone has known, the building section has accounted for 1/3 of the primary energy use in the globe. It's comparable to manufacturing, field, and transportation. It's rather significant, isn't it? So we have to really think how could we deal with these situations and how could we solve and improve and mitigate the problems nowadays. Next, Julia, please. I believe there are 3 pillars of energy efficiency when we talk about this this topic. So we have to always think about the climate in the first place and combine the cover of the buildings, the envelope, and finally we enter into the buildings. Inside of the buildings, the service systems, we have to always think about all these 3 aspects, and in order to reach our goal, the energy efficiency. All these aspects need to be put on the table. This is because it's quite often when we talk about our investor or clients, they might think, I heard that there are quite interesting technologies I heard is very successful in Japan and Europe or in US. How about we use it in our project? This is very common situations. But as professionals, we always know there are limitations. The technology cannot be used as we will. So we have to look at the 3 pillars always. Next, Jimmy, please. I use this diagram to show the information flow and feedbacks in different stages of the project, the building life cycle time, and how could we get the lessons learned in the previous project and use it for the future project in order to keep improving the energy efficiency based on the knowledges we gained. Energy efficiency in buildings is a life cycle process. From the right beginning, from concept, design, construction, and operation, of which certainly the design phase is very important. If you set off in wrong directions, then basically you're away from your target from the first minute. And in the later phase, when you try to correct your mistakes or some problems, then you have to pay a lot more. Because when you have to stop your business, you have to really think how to reset your schedules to simply retrofit your interior. You change your envelope or change your glazings or replace your mechanical terminals. All these changes and renovations will take a lot of efforts additionally, which could have been solved in the beginning when we have a thorough shot of the holistic design. And it's a topic that needs to be addressed throughout all stages of the building life cycle. Next, Jimmy, please. Climate, the locations means the location of the project is crucial. So here I refer to Köppen's classifications. Apparently, it's a German name. There are 5 typical climate zones in his classification method. Jimmy, could I have next slide? That is tropical zones, dry zones, temperate, and continental, and polar zones. A good technology is always bound to these local conditions, the geographical or climate conditions, always, because you cannot really, as I just talked about, you have to combine your project's local limits and constraints. And always refer to a good standard, a well-acknowledged standards by professionals in this field. Jimmy, can I have a next? For DMC countries, the ADB DMC countries, unfortunately, most of them located in 2 zones, and tropical zones and temperate zones, so that we can put our focus and efforts on these 2 zones to find good solutions. Jimmy, do I have next? Envelope as a cover and the skin of the buildings. It contributes 1/3 of the heat gains and loss. So that's why it is important always that we control demand, and by reinforce the insulation layers, the thickness of the insulations, the material of insulations. All that should be well considered. Besides that, we look at thermal performance factors like the shape of the buildings, the orientation, the shading equipment, and ventilation, air tightness. There are many factors, and input can make a difference at the end of the day. So we really need to use holistic way, put all these inputs, as far as I know, into a simulation software and find the results and find their influence and impacts, so that we can find the major troublemaker. And this is the diagram. I use this diagram to show the actions in different stages. So for design stages, I prefer at least to use multiple simulation tools, including but not limited to CFD and dynamic building and simulation software. All of this and daylighting simulations. All this simulation software can help us to understand deeply what the real performance after build outs. And in the later phase, I prefer use I suggest to use the submetering method or the system to facilitate the improvement during operations. This is the control domain. We use this tool thanks to the modernized technologies, which can help us a lot later this. And in this functional commissioning process, we always use develop engine management and information systems. It also control tools. And yeah, this information system can help us a lot and help us diagnose, help us collect informations, report the current situations. And Jin-Yao, could you roll back to the last slide? And also the training of the FM staff is also very important because they are the real users of the building. If they are not well trained, they don't understand the building, how to make a good performance and best performance of the buildings, nothing can really help in the end. Okay, next slide, please. So besides the cooling and heating systems, then we come to renewables. And renewable means how can we use the natural resources and implementation and maintenance combined with the other factors like incentives and local regulations, constraints, and characteristics of the energy profile. It's not only solar, but also wind, wave, geothermal, and biomass, other, yeah, and so on and so much. But the most popular, of course, is the solar and geothermal. The renewable energy system then has to be standalone. It can be hybrid systems. So the renewable system combined with the building structure, for example. In that case, the engineers should work with architects in the beginning, and yeah, make the solar, for example, the solar chimney, the solar trunk wall. These are all good examples coming out the collaborations between engineers and architects. This is on the building level. Of course, when we look at the large scale, the district scale and urban scale, then we need to look at the building, the energy storage, and how to use the waste heat from the manufacturing facilities. How do we distribute the energy in an efficient way? So this is another topic, but it's closely related to energy efficiency at the building level. Next slide, please. Yeah, this is a diagram. I use this to show the typical technologies of the energy efficiency strategies. There are a lot over there. Some can be used always, anytime, as long as you wish. But most of them require careful evaluations and analysis. Yeah. Next, please. Yeah. Finally, we come to this disease resilience of the system. It wasn't a topic. It wasn't really a concern before this coronavirus pandemic. But now, after 2 years suffering, we know what could happen if we don't design a good air conditioning system in the beginning of a building project. We have to consider this concept and include this concept, make our building adapt to the pneumonia and other respiratory infections like this COVID-19, so that the mechanical system can quickly be adapted to the new situations. For example, this large open office could be quickly renovated. The small chambers, like be flexible partitions during a pandemic. But it's not that simple. Just put some glass and a glass wall in the corridor, then everything up and running. It's not that case. We have to make sure every chamber and every cabin can be handled, can be conditioned by a good system, and can be ventilated. So the mechanical system, HVAC system, has to be prepared in the beginning. That's we call disease resilience. This perhaps is not in the domain of energy efficiency anymore, but it's functionality of the HVAC systems. So it's also very important in our project. Next, please. Yeah, a quick summary. Reducing carbon emissions has become very important nowadays. Particularly this year, Europe, like Germany, they have this flood hazard. They have, and in US, they have wildfire situations. A lot of people died and property lost and people injured and lost their homes. This years is really turbulent. Not only in the climate, but also in many other aspects. So that's make all the professionals like Jimmy just pointed out, reduce the carbon emissions become never more important than this year. And in the DMC countries, developing member countries of ADB, I believe 20% improvement in energy efficiency over the local standards is rather easy to achieve simply by utilizing a good thought, a thorough considerations by the designers, a well collaboration between the engineer and architect, a good understanding of the methodologies of energy efficiency. And the design should also integrate and include a special chapter to cover its disease resilience capabilities, which only makes sense when the flexibility can be talked and discussed and also included in the first minutes when we start off the building's preparations and discussions. This is very essential. With this note, I conclude my speech today. Sorry for the delay in the beginning. Next, I would hand over my microphone to Professor Sika. He is currently a professor and programmer director and co-director in the Department of the Built Environment at the National University of Singapore. He is also founding director of Enhanced Air Quality Company. His research interests include thermal comfort, ventilation, IAQ, airborne infection control, energy efficient HVAC systems, and building energy analysis. He has about 300 publications, wow, in this field, in international journals and conferences. Welcome, Professor Sika.
Thank you, Dr. Yang Peng Zhao. I can share my screen now.
Yes, yes.
Okay. I just want to make sure that you are able to see my screen in the presentation mode.
Yes, please put it in full screen mode.
Yeah, I'm just coming to that. So just something on my. Are you able to see?
It's good. Please go ahead your presentation.
Is it in full screen mode?
Yes, please
Okay.
go ahead.
All right, thank you so much. I would like to thank the ADB and the organizers for this webinar. It's a very important topical theme that we are discussing today. I'm going to be speaking on emerging HVAC technologies for energy efficient, healthy buildings. And the focus will be on hot and humid climates or the tropics. I'm sure when you look at a slide like this, the keywords are all in there. We're looking at the building performance in terms of its energy and sustainability goals, greenhouse gas emission reduction, and one important word that I now find extremely useful is the word resilience. The previous speaker alluded to that as well. Then we have the human requirements inside the building that relates to the health and the well-being aspect of it, the thermal comfort, indoor air quality, visual comfort, oral comfort. And if we try to look at it from a building block, so to speak, here, what constitutes resilient buildings? We could be seeing innovative design, adaptability, operational flexibility, an important keyword, at least in my mind. We may have systems designed in a particular way, but we can make it to work differently, make the system flexible during the operation. That would mean we need to have systems that are modular in nature, components that can be turned on or off depending on our requirement. The space use, changes in space use perhaps. Again, alluded by the previous speaker when he mentioned about being able to change an open plan space into cubicles or with partitions. And then I find an important word that I resonate very closely in today's context with the COVID-19, the normal mode and the resilient mode. I'll come back to that later as we go through the presentation. Let me start off by showing you a couple of slides and saying a couple of points about indoor air quality in a very, very overview context. I like this quote from Pettenkofer, the German chemist. It says it all. It says that if there's a pile of manure in a space, don't try to remove the odor by ventilation, remove the pile of manure. Source control, the first and foremost thing that we should strive for. And then, of course, you've taken care of most of the sources in the building, and then you still have to handle the exposure to the occupants. That's where ventilation comes in. Ventilation using outside air, filtered and cleaned, and use that to dilute the indoor contaminants, because there will still be contaminants released by the various sources indoor. This slide really is at the key and the heart of what we are going through in the whole world with the big challenge that the whole world is facing in terms of the SARS-CoV-2 spread. And this is talking primarily about the airborne route of transmission. What we're seeing here is there could be the droplet mode, which can just fall within a certain distance of 1 to 2 meters. Then there is a short range airborne transmission when two people are close to each other, when they sing, when they talk loudly, whatever happens in terms of the vocalization activity, there could be transmission. And then there is long range transmission within the room. Now look at this in the context of a room. How much air is supplied, how much air is removed, the ventilation, the dilution plays a very, very important role in the mitigation of infectious aerosol spread. Let me now come very specifically to ventilation and room air distribution, because that's really where my interest is and how we can relate that to the fundamental requirements of human needs, thermal, air quality, and all the various other points, especially in the context of infectious aerosol transmission mitigation. Current practice, we have mixing ventilation, ceiling supply, and then it mixes within the room, and then we have air extracted from the room. Then we could have displacement ventilation supply from the floor level or the low height of the wall. And due to buoyancy, the air rises and then it's removed from the space. Very common in European countries, not so much in the tropics. Underfloor air distribution, again, supply from the floor and removed from the top. Now, in all of these, you will notice that the indoor airflow distribution plays a very important role as to what's happening. Let's look at what is needed with the ventilation air. Quality, how good it is. So we know that there are several parts of the world where the quality is a challenge. We need to clean it, filter it, and remove the particles and those kind of requirements. And then we need to provide a certain minimum amount. And then the distribution is the one that I want to focus on. There are things related to how effective it is and how we can reduce the contaminant exposure to a person. So all these are indices that you can read from my handout material. I won't go into the details here. I'm going to come very, very specifically here to some of the adaptable and resilient systems and strategies, especially in the non-residential building context. I'm going to go very quick. It's an overview, not going into too much details. My fundamental thinking here, my fundamental strategy would always be separate the ventilation from cooling and or heating. So if we can handle these two needs separately, that's the ideal way. That's probably the most energy efficient way of doing things. So here we're talking about a dedicated outdoor air system and a secondary system. Dedicated outdoor air supplied to the rooms, to the occupied zones. It can be used on demand, depending on what the people need and how much they need. We can control it, make it work the way we want to in the most efficient manner as possible. And likewise, for the thermal comfort requirement, the thermal needs, we can use the room air, the recirculated air, and do great things with that. We don't have to move all the room air to the air handling unit, the central AHU. Why can't we handle that within the space? There are technologies that do that, and I'm going to be talking about some of those as we go along. Something that we developed in our own group some 20 years ago. At that time, we were thinking basically, why have everything mixed in terms of supply air? Let's separate it. We call that the single coil twin fan air conditioning and air distribution system. I don't have to do much more than just press this button to show what the concept is. one air handling unit split into two compartments, same cooling coil, two different filter compartments, two fans, you're actually handling the ventilation distinct from the recirculation. And what that does is it allows you to accomplish what we call demand ventilation in individual occupied zones. So if you have a central system, you can actually manage your individual zone requirements depending on what you need, because you now really have two air streams that you can manage with. And then a lot of us would have heard about the heat pipe technology. It's a passive energy recovery technology, if you like. A conventional air handling unit, this is a cooling coil. We wrap around a heat pipe around the cooling coil. There is the evaporator section, and then there is a condenser section. Basically, what this does is it picks up the heat from the incoming outdoor air and transfers that to the overcooled air on the downstream side of the cooling coil. Basically, you're moving heat from here to the downstream of the cooling coil. So you're making use of, in a way, recovered energy, if you like. So you can achieve better cooling and dehumidification with something like a heat pipe. And in a couple of studies that we have done, we were able to quantitatively demonstrate about 18 to 20% energy savings purely on the fact that you do not need a reheater downstream of the cooling coil to achieve your temperature and your humidity control, so to speak. Personalized ventilation, something that I really want to talk about very, very quickly, something we have found a lot of benefit in. We get the outdoor air directly to the person's breathing zone, and that helps tremendously. Thermal comfort, indoor air quality, mitigating the airborne infection spread, certainly in situations like the COVID-19 problems that we faced globally at this time. As I said, the idea is to get the outdoor air, the fresh air, directly delivered at the occupant breathing zone. And of course, the benefits are, as you can see here. We tried several different configurations. I'm just going to share with you one of them, maybe a couple of them here. What we call a desk-mounted personalized ventilation system. PV here is personalized ventilation, not the other PV that most of us might be familiar with. Integrating that with the conventional ceiling supply mixing ventilation system. This one slide, I just want to highlight what is the purpose and significance of ventilation effectiveness. It's the effectiveness with which the fresh air, the outdoor air, can remove the contaminants from the occupied breathing zone. So the higher this number, the better it is. So you notice that when we have personalized ventilation system, we were actually able to measure through tracer gas studies and quantify that we have a higher ventilation effectiveness. Compared to when we did not have personalized ventilation, it's about 1. So obviously PV systems, personalized ventilation improves or increases the ventilation effectiveness. When we do that, we are able to maintain your background temperatures warmer, 26 degrees or whatever, even higher, and then maintain your comfort and air quality with a small amount of personalized air being delivered at the person's breathing zone. So obviously there's energy saving from that angle as well. Another configuration of personalized ventilation system coupled with chill beams. Chill beams, again, as you notice that these are, water-based system, chill water supply to the occupied zone, heat exchanger or the beam that is maintained there at individual zones. So we said, what happened if we use the personalized air, the outdoor air, to operate the chill beam? And we find that we could actually get a total energy savings of about 16%. Where does all these savings come from? Look at that, the distribution fans. We don't have a return air to be transmitted or moved around. So transport energy is considerably reduced. And the fact that your background temperature can be maintained warmer. So we did through a CFV simulation study, conventional VAV system everywhere in the room, 24 degrees Celsius. And when we have a personalized ventilation combined with an activated chill beam, 27 degrees, we let it stratify in the space, but in the occupied zone, we maintain a cooler environment, all made up of 100% outside air, so people like it from the point of view of air quality as well. And then, as we say, this also helps in contaminant concentration plus stratification as well. That's a nice thing that we found over there. A third extended kind of a concept was we combine personalized ventilation with local exhaust. Why don't we remove the contaminated air that comes from an infected person with, say, COVID-19, if we can extract it locally, personalized exhaust? So this is our experimental setup. We use mannequin in our studies. Here is a breathing thermal mannequin. So this mannequin is the patient coughing out, or not exactly coughing, but spitting out infectious aerosol. We use a tracer gas, like say CO2 in this case, to mark that, and then see how much of that is being inhaled by this mannequin. And we have all this, shoulder, we call this the shoulder exhaust, and then we call this the head exhaust, top exhaust. And we found when we have this exhaust operational for the patient, if this is a doctor, let's say, the exposure of this infectious aerosol is considerably reduced for the doctor. So basically, we can conceptually think that when we have local exhaust, it's going to work. And really in our studies and all these publications, we're able to demonstrate that. Finally, towards the end, I'm coming to something that we are extremely delighted to have in our own backyard in our university. We have something called a DOA system, a dedicated outdoor air system that's coupled with ceiling fans. This is our building, the first purpose-built net zero energy building in Singapore. It's our own school building. We call this the SDE4. And what we do here is this concept of hybrid air conditioning. Conventional system, that's the one on the extreme left, 24 degrees Celsius. Everything is, normal comfort, air quality, energy, you can say 24 degrees, normal refrigeration-based compression, vapor compression system is going to be energy intensive. Conventional AHU, what happens if you change this temperature, make it 27 degrees? Energy, yeah, we are happy, but then not quite for thermal comfort and indoor air quality. But when we do this, 27 degrees, and we have 100% outside air system delivering, and we combine that with ceiling fan, wow, the story changes. People like it. Our studies here in this building with occupied people, students in the studio office, studio rooms, and in the studio classes, they like it. And we have another, I have another presentation exclusively on that, but we have no time to go into the details. All I can share with you here is hybrid system works. In SDE4, we have had data that supports that kind of a study. I just had one of these field measurement study of ours just to give you a sense that S1 to S4, these are our studio classroom areas. Look at the temperatures, they are 26.5, 26.7, 27 degrees, and humidity RH about 58 to 60% RH. And all these environments, when people are there, we have the fan, ceiling fan running about 1 meter per second. People like it. It works. It just works beautifully. Filtration and disinfection is another HVAC system related strategy. In ASHRAE, there's a lot of information on COVID-19 response resources. You can use my PDF handout and the link that I've provided for you, and to look at some of the details. We did some studies several years ago, 5-6 years ago, pre-COVID time. The idea was, when you place a UV system downstream of a cooling coil, what does it do? It keeps the coils clean. It helps in energy performance. That's what we see here. Y-axis overall thermal conductance after the UV, it's higher. And again, the air side heat transfer coefficient increases after the UV. So UV really helps to keep the coils clean. And by the way, as we say at the time, in addition to surface and condenser water disinfection benefits, the coil irradiation systems also helps us to keep the airborne infectious aerosol mitigated. In other words, there is a collateral air disinfection benefit that we get from UVGI system. I come back to my last slide. My final remark is going back to my very first or second slide. We need to have resilient building concept. We need to think about innovative design. We need to think about systems that can be adaptable, operationally flexible. Think about modular systems. At the component level, can we use them and not use them depending on our needs? And I think that's what will help us accomplish what we may want to call as a normal mode of operation, and perhaps a resilient mode depending on what happens in the future. We are still not out of the woods yet in this pandemic. We should be prepared for what happens in future buildings, designs, and in, say, 5 years down the track, 10 years down the track, buildings really need to be resilient to provide an energy efficient and healthy building for people. Thank you for your attention.
Good. This is quite interesting presentations. Particularly, there are some shining points like DOS system plus ceiling fans and personalized ventilations. As far as I know, Google used the personalized ventilations during this pandemic in their headquarters in US, and also this heat pipe use heat pipe technologies to offset reheat technologies. Wonderful. And also like your metaphor about this manure and all those. So thank you, Chandra Sikha.
My pleasure.
I would invite the next speaker, Dr. Ala Olama. He received his PhD in 1980 from Faculty of Engineering at King's College, University of London. In absorption refrigeration, he has been a member of a prestigious refrigeration, air conditioning, heat pumps technical options committee of the United Nations. He has been instrumental in the establishment of the first 2 district cooling company in Egypt. Welcome.
Thank you very much, sir. I'd like to thank the organizer of the seminar, in particular, Dr. Yash, for his efforts and for his kind invitation. I will talk very briefly on the new technologies that are used in particular when you are considering not in-kind cooling technology. So to start with, if you look at the different refrigerants nowadays, you'll find that the majority of the refrigerants are in the category of A to L, which are refrigerants that has some flammability. And this created problems in many instances where the codes and the standards are not really geared to deal with refrigerants that has flammability or some toxicity. So this is why we started looking more closely at the not in-kind cooling technology. And the report of the Refrigeration Technical Option Committee that is published every 4 years talk extensively about those systems. So the report has 13, it used to be 12, now the new one will have 13 different chapters. In chapter 12, not in kind technology, talks about different technologies that are used. I would like to talk extensively about that because very few of us are familiar with this sort of technology. We are more familiar with the mechanical vapor compression system and with the systems that do not utilize anything but electric energy to produce cooling. Not in kind cooling technology are those technology that utilize some electric power, but the majority of the power is coming from renewable sources. And by definition, this is a more sustainable system, a higher efficiency system. Of those technologies, possibly one of the more developed kind is system using natural gas-fired chiller to produce cooling, absorption chiller, and those using reject heat, such as exhaust and refuse energy, to fire a system. But in particular, if we want to look about not in-kind cooling technology, I think one of the most important ones are grouped here in 17 technology. Those technology are widely available technology. In other words, if you look at the definition of not in-kind cooling technology, you'll find those that are available. This means that only one manufacturer is doing them. Widely available, this means that are produced by more than one manufacturer. And then you have the 2 other classification, which is emerging technology that has passed research and development, but are not really there yet, and those in the research and development phase. If you look at the life cycle operating cost of those 17 technology, you find the one on the right, the conventional system, will produce a ratio of between 2 and 2.5 unit price, this is ratio, per ton hour. But the more you go to the left, the better technology, the more efficient technology it is. Down to the most efficient, which is the exhaust recovery absorption machine. In this graph, there are those that you can use for district cooling, which are represented by a red triangle. And those are used only for central air conditioning, but not particularly in district cooling. But by using a district cooling system, if you have a large enough capacity, a large enough density of capacity, then you tend to reduce the bank of refrigerant used, which will make it a more efficient technology by definition, because you are using less refrigerant. The two that I'd like to look at here in particular are those use deep sea cooling and those that use direct, indirect evaporative cooling. Now, those technologies, if you look at a city such as this one, you'll find that you could, with a district cooling system, utilize the heat that is rejected from some buildings into firing other absorption machine and getting cooling for other buildings that need cooling. So eventually, the idea, the utopian city will look like that. It will have connected to free source of cooling, like it is shown here in this caption on the far right. And it will use waste incineration to fire other system or to get heating. And you'll have a connected renewable energy generating on one side. And you are connecting the commercial demand with the residential demand, because they are not necessarily happening in the same time. And you'll also get some solar cooling connected to the district heating system. And you are capturing heat from sewage and waste heat, or you are using absorption chiller from waste heat to produce cooling. And you combine all that to get the cooling and heating demand for this particular place. Now, let's look at the deep sea cooling. This is a study that we are trying to implement now in Egypt by using the deep sea to cool buildings. And in order to do that, let's look quickly at deep sea cooling. In deep sea cooling, you will get water at lower temperature from the deep depths of the sea, go to a certain station, the one shown in the middle of the slide over here, make a heat exchanger over there that will take the water, the enthalpy of the water, and cool the closed circuit chilled water system, and hereby cool a certain area. Now, this can also be done by laying pipe at certain depths. In particular, if you go down to lower than 1,000 meters in the sea, in an open sea, you will probably get temperature in the range of 4 or 5 degrees C. So you will take here the water from the lower pipe over there, go to a heat exchanger room, do the exchange between the water coming from the sea and going to the city, and then reject the heat, the seawater heat, at the surface, at which the temperature of the water is the same as the temperature you are sending back to the water. And by doing so, you are taking care not to affect the marine life. This is what we are proposing for this city that has 35 coastal towers in Alamein, at the north coast of Egypt, where we are using the same concept to produce cooling. Now, looking at this city in particular, you'll find that there is, what is proposed is a couple of lines of chilled water pipe going all around the coast and cooling the water. And by doing so, sending chilled water to each and every tower over there with a plant location in the middle. Now, this system combined with a direct, indirect evaporative cooling system will give us the sort of things that with it, we can combat the advent of COVID-19. And let me go back to the first slide where it shows the life cycle operating costs. If you look at number 15 in this slide, which is direct, indirect evaporative cooling, you'll find that when using it with a central system, your life cycle operating cost goes down to 0.9 unit price per ton hour. In a conventional system, the same unit price is somewhere between 2 and 2.55. So the saving is really very high. But what is a direct, indirect evaporative cooling system? A direct, indirect evaporative cooling system is very much a system, maybe has a lot of similarity with Dr. Chandra Shakhtar's system, which is a dedicated system, whereby you would use on this graph the left side of the sort of schematic diagram of the unit, where you use air to cool in a cooling tower arrangement type of system, water that is pumped to the right side of the unit. And this colder water, if you like, would cool air coming from the primary air, coming from outside, and then it will reduce the temperature, the dry bulk temperature of the air, and then you go to a second stage. And this second stage has a sort of an evaporative cooling procedure where water is sprayed in the stream, so it reduces the air temperature to levels that are similar to the one that is needed for air conditioning. So if you look at the psychometric chart, instead of going sort of horizontally, on this dotted line and cooling by evaporative cooling only, where you reduce the dry bulk temperature to a certain level, but you increase the humidity also. Now you'll go horizontally and then adiabatically. So you have two processes of cooling. And by doing so, you reduce the temperature of the air coming out of the system to the levels that are nearer those of a DX system or a chilled water system. The trouble with this system is that you need a dry ambient to do that. So if you imagine a third coil somewhere before the blower, when this system is connected to a chilled water system, then you can actually reduce the temperature of the air at will, at a higher humidity. We tried this in Kuwait City, and we find that Kuwait is known for being very dry in summer and extremely high in summer air temperature. It's one of the HAT cities, high ambient temperature city, as defined by the United Nations, where temperature can reach 52 degrees C in summer. So by having a hybrid system, added to it a coil just before the fan over there, so you will go down to temperatures that are quite low, even if you have a relatively humid summer. So the efficiency of this system, combined with a central system, you can go down to efficiency, you can achieve 20 to 25% at will. So if we are starting to design a new system, taking in mind COVID and the problem of cross-contamination, a full fresh air system, this is a full fresh air system, a full fresh air system such as this one, added to it a DX coil or a chilled water coil, will get the air going in one direction, reduce cross-contamination to a minimum, and also reduce efficiency. Increases efficiency, because the system uses evaporation, direct, indirect evaporation, to get you the efficiency that you are looking for. So what we are recommending now is to use a direct, indirect evaporative cooling system tied up to the sort of system where you get your chilled water originally from one of the 17 technologies that I talked about at the very beginning. And by doing those two combinations, we can reduce cross-contamination to a great deal. And also by doing that, we can increase the efficiency of the system. Thank you very much.
Thank you. It is quite interesting presentations, and I noticed this Deepsea Cooling system, for example. I think that is a variant of geothermal heat pump systems, kind of. But I do worry about the cleaning, maintenance, and investments, and how realistic we could really use for other projects. And you mentioned there's a large distribution network of the chilled water pipes that might also evolve the concerns of the insulations and the loss on the transportations. Also, you mentioned evaporation systems, direct and indirect. That's wonderful applications in the desert climate. I heard 2,000 years ago, the Roman has used this prototype, maybe not, of course, not that organized, but used the prototype in the desert for the evaporation systems.
Yes.
And although I'm not quite sure, I understand the in-kind and the not in-kind terminologies in your PowerPoint. I would chew it up and come back to you if I need. Thank you, Dr. Alam. I would like invite next speaker, Mr. C. Subramaniam. He is an independent consultant at 3S Green and 3S Consultant, Bangalore, and offers consulting services in the fields of sustainability, HVAC, and IBMS design services. He has handled projects related to HVAC and AR, intelligent building automation system and controls, chiller plant management, district cooling, data center applications, green buildings, etc. Welcome to have a speech.
Thank you, Zhu. I'll share the screen.
Yeah, please.
I hope the screen is visible. Yeah. Good morning, good afternoon, and good evening to everyone, wherever you are from. Thank you for the opportunity. Thank you, Yesh, and thank you, Zhou, and thank you, Dr. Zhu Zinmeo. Now, in the next 15 minutes, I would like to share with you the various aspects of energy efficient centralized air conditioning system that we are talking about. And for doing this, what I want to do, I've just laid a few points, as general agenda points. One is first we'll go to have a quick overview of the energy spread in commercial buildings, which the other experts shared as well. And then we will go through the best design practices, in the energy efficient systems, and then how an integrated comfort system and earthwise, system helps us to do it. And then look at also various energy efficient strategies that we need to adopt, and possibly look at a couple of alternate design concepts and innovative methods. And once we do all this, now how do we ensure an operational excellence in building energy efficiency from the HVAC point of view, and on a sustained basis on a year-on-year, what we are talking about. And when we look at this, we do know that there are commercial buildings, there are owner-occupied buildings, there are tenanted buildings, because we are talking about the developing economies, the developing countries we are talking about. So we have various kinds of buildings where the approach to the project, approach to the built space, built environment is a little different from every aspect of the owner and developer. Now, on this energy spread, which we all know, it varies possibly between 50 to 60%. And this is by ResearchGate, and various research organizations do carry out for commercial buildings. Possibly we are looking at HVAC, the cooling and heating, consuming a sizable portion of an energy matrix in a building. Now, while we say that, yes, there's a lot of opportunities, and how do we handle this huge varying load? Now, we have to understand one thing, that this load is not constant throughout the year, throughout whatever the number of operating hours of in a building. You take it as 3,000 hours or 5,000 hours or 8,000 hours in a year. The load, the heating load, the cooling load varies throughout. So the first and foremost thing that we have to have in mind whenever we are designing an air conditioning refrigeration system for a building, possibly we have to look at analyzing the load of a building, heating and cooling load on a complete year basis. As my friend said about energy simulation, it gives us the data of how the entire, throughout the year it pans out, and then possibly keep the options open on mixed mode kind of, systems, which will ensure that maximum efficiency of various systems can take us through the integrated system efficiencies. Now, coming back to the basics, wherever technologically we are today, in air conditioning refrigeration system, we are talking about this five loops: the air side loop, the chill water loop, the refrigeration and the heat rejection loop. And the one that connects all these loops is the controls loop. And then each and every component in this diagram, what you see here, it contributes to the performance of the building, as well as it impacts the performance of the other equipment. And as a system, we are talking about the efficiency there, which means it's our responsibility to understand the performance of each and every equipment component and optimally design it, optimally monitor it, and ensure that it does it. Now, when we look at the best design practices, what are the design practices? One is from the air side, one other is from the chill water design side, the another is chiller plant management controls, condenser water piping design, refrigerant and environmental aspects, and equipment and system selection aspect is what we need to possibly go through systematically to ensure that the entire system is optimally designed. Now, when we look at the air side, we do have various options. We have constant air volume system, we have variable air volume system, we have treated fresh air systems, demand control, ventilation, and economizers, right? Now, each one of this, gives us an opportunity to harness the outside ambient condition, ensure that we optimally design each one of this. Now, when we talk about the variable air volume system, yes, it's a great system. It has to be properly designed, properly factory calibrated. These are the things that we need to take care. It provides us good comfort level, and it's very prominent, very prevalent in the built environment space in the building and construction industry, because it's easy to build, easy to install, easy to operate, easy to control and monitor as well. But there are some good points that we need to take care. Like, for example, you see here various rooms which are being air conditioned using the variable air volume system boxes. Now you have a constant supply air temperature, which is given to the VAV box, and then each of these zone sensor handles that. What are the precautions that we should take is this element, what you see here as a pressure sensor, duct static pressure sensor. Now that set point is what defines the variable frequency drives, the energy consumption of the AHU. So which means these need to be commissioned properly, and we have to go back to the system again once the occupancy happens. Because normally a building, when it's commissioned, possibly it may not be fully occupied, so the set points may be different, the performance of the equipment may be different. So these are some of the ground realities that we need to know. We need to understand when we design, operate, and commission and put the system into operation. Revisit the thing back, get the set points back again, and then ensure that the design stage, whatever performance that was estimated, the same thing is what we are going to get, right through the life cycle of the equipment. Now, coming to the similar application on VAV boxes for various fresh air application, because you have multiple floors, multiple levels in a building. And then you have occupancies, shifting from one level to another level. We see all this every day in and day out. And we have to, have a good amount of fresh air. Our other expert talked about how it's very important. Now we are talking about disease resilient. We want to have a good, indoor air quality systems there. So which means that we want a responsive system. So how is that possible for demand control ventilation? So we have to have the things designed as per ASHRAE and ventilation standards of local conditions, codes and all that. So we need to ensure that based on the occupancy, the variable air volume system, the controls component also gets, it delivers the amount of air, which is fresh air, which is required, because fresh air contributes a sizable amount of cooling and heating load into the equipment, what we are talking about. So this is a major component. So we have to have enough demand control ventilation, the indoor air quality sensors, which will take us possibly through proper operation of these fresh air systems into the building. Now, on the room air diffusion methods, we have lots of methods. General practice is to use mixed air systems, but we do have displacement systems and underfloor air distribution. But in different developing economies, some are more prominently used. So while we use that, we have to slowly start creating awareness for them to move from mixed air system to displacement system, because you see here, displacement systems, you have supply air at a higher air quantity, higher temperature, the low velocity. So the IAQ also is better. So many other advantages are there with different room air diffusion methods. So it's always good to ensure that ensure that the designers, ensure that the owners and contractors, they are all shifted to much better systems, more efficient systems that are available today, technologically available. So the under airflow distribution. Now, coming from the air side to the chill water side, we are talking about various aspects of primary, variable, primary, secondary, variable system, variable, primary. We do have series counterflow systems and high delta T systems on evaporators and condensers, and heat recovery chillers, because those are very important based on applications. If you have a healthcare industry or a hospitality industry where there is a requirement of a heating and cooling, where there is a requirement of hot water, as well as there is a parallel need of a cooling as well. So we need to ensure that the coefficient of performance of the entire system is kept in mind, and then you design the entire system so that you get the best out of the entire equipment what we are talking about. So now looking at the high delta T systems on series counterflow, because when we talk about large systems, you talk about 10,000 tons, you talk about 20,000 tons, either a centralized air conditioning system or a district cooling system. It's possibly good to do an analysis on, compared to a base case, how a series counterflow is going to help us, because the lift point, what we are talking about, contributes directly to 15 to 20%, 18, 19% saving on your power. So that correspondingly, sizable quantity of power consumption on the main equipment, because we talked about 50 to 60% on the HVAC, and out of that, the chiller plant consumes a large chunk, and chillers consume a large chunk of energy. So even if you save 20%, it contributes to almost 5 to 6% of saving on the overall energy performance of the building as well. Now, on the district energy systems, district cooling and heating systems, the main thing is we do take care of the diversity which is there. So your entire demand, power demand comes down, your cooling load, average cooling load, the equipment energy efficiency, the operating points at which the equipment work are much higher, much better. So you can ensure that the performance is at the peak efficiency points we are talking about, and we can always harness the renewable energy. And our expert talked about drawing, water from so those are the other options which are there on the district energy systems as well. And so the load determination is a major important point here. So whenever we bring in, so when we have, for example, 5 to 10 chillers in a building, we should, on a ground reality basis, we are not supposed to work any chiller for any number of hours more than what it is required to operate. That is where the energy bill is going to get the hit. So it's very important that a chiller plant management system is installed properly and operated, and the load determination takes care. Now, while we design this, the chiller cooling tower balancing is another tricky point. The chiller, as we know, the performance depends on load, the condenser water entry temperature, and chiller design. So the cooling tower, the performance depends on the wet bulb, the load on the cooling tower, the condenser water temperature at which it enters and leaves, and tower design and approach. Now, enough good amount of research has happened where there is a common temperature at which both put together the energy can be optimized. And that's what we are talking about, the optimum chill condenser water temperature, because the curve goes down and then at an optimal temperature, the energy of chiller and tower together goes up. Now that is where the control system has to capture that condenser water temperature, and which is the optimum condenser water temperature at which the system can be designed to ensure the peak performance of the combined load of the thing. So whenever we design an equipment and system, we should ensure that the equipment is, because today technology has gone up tremendously. We get the best of the technologies, best of microprocessors, best of chillers. We have to ensure that the chillers for the best application is designed, and also the system is selected properly, right? And then looking at this option of low flow and high delta T, how does it help us in the system, in the air handlers, the duct work, and piping and pumping? As the supply temperature, we say chill water temperature goes down, your temperature differential goes increasing, the flow rates of chill water flow, condenser water flow, the airflow goes down, the fan sizes go down, the duct sizes go down, the pump size goes down, piping size goes down. So this is where we are talking about an earth-wise, integrated comfort system, more efficient, resilient, and on a long-term basis we are talking about. So when we go into the water side, we have an option of heat recovery, geothermal, cogeneration, thermal storage, and air side. And then looking at alternate designs, we have radiant cooling, ground source heat pump, earth air tunnel. These options are there. But again, it depends on the ambient conditions and the location of the building, which we have to work on mixed mode conditions. So thermal storage, it gives you great benefits. It shifts your peak load. It reduces the air side cost, and it pays back, right? So you're freezing cooling the thing when it is the ambient condition is lowest, and harnessing it, and for optimum performance output from your entire chill water air conditioning system. Then you have air side recovery, water side recovery, which again we talked about. And radiant cooling system is one of the best, and evaporative cooling our expert talked about, which is option is there for us. High efficiency equipment gets designed. Now this is one of the buildings where we talk about a traditional conventional, two buildings were set up with, one is a conventional design and one with a radiant cooling system. And you see here the plant kilowatt per ton is almost around 30% less compared to a 0.68 kilowatt per ton of a conventional one. You're getting with the radiant only 0.44. So which means definitely, the innovative alternative methods of cooling and heating provides a great amount of energy saving opportunities for us. And we have to always remember that meter is on the building and not on the equipment, because it is always good to get the end system right. And in addition to the equipment, also one of the best. And the basic rule always works: measure, monitor, and control. What cannot be measured cannot be controlled properly. Energy metering, logging, very important. So coming back to this, it's very important to handle each and every component of this loop at optimum level to achieve the energy saving for us, to keep the total cost of ownership down to, based on the life cycle cost analysis. It is not just the first cost. There's so much of hidden cost lying below the level. And to get a smart building, smart system, smart city, we have to have a systematic integrated approach, measurable, controllable, achievable, recurring, and total cost of ownership is very important for us. So I think in the last 15 minutes, we have shared some of the energy spread, what are the best energy efficient systems, earthwise systems options available for us, and energy efficiency strategies and alternate design. And to achieve operational excellence, it is very important to have a good data collection, analytics done, and all that. So we look forward to getting the question session. Thank you so much for the opportunity given for sharing my thoughts in this forum. Thank you.
Thank you. There are a lot of aspects in the building has been covered in these presentations. For example, this VAV systems, it could go wrong. For example, it's low when it goes to low load profile and fully controlled. Sometimes it cannot be work well with the water loop. This has to be well evaluated and well designed. And also, as presentation mentioned, this VPF systems, variable primary flow system, the primary secondary flow, variable secondary pump systems. I personally witnessed a lot of problems on these systems on the site, and I was invited to fix these problems. So this is a cool thing of the HVAC topic, because this is really involve a lot of factors, a lot of systems, 5 loops, as Mr. Samania he mentioned. This is quite complicated. I hope our digital evolution, the digital technologies can help us to conquer these common problems in the design and the constructions and operations. With this speech, we conclude this energy efficient CAC systems today, but we do have a QA session. Now I would like to hand over the screen to Dr. Yash for the next session. And welcome.
Thank you, Dr. Shah.
Dr. Yash?
Yeah, thank you for all the speakers for the wonderful session. We have very little time for the question and answer session, but I would go through one question for each speaker. We have 4 or 5 questions, and I know some of the speakers have answered it, but I think it will be helpful to put it to the larger audience. The first question is for Professor Chandrasekhar. Professor, this is the question that you answered, but I'd like everybody to know your answer in terms of what's the benefit of having an air conditioning system controls, where one option is to operate it at 27 degrees with fan, and the other option with 24 degrees the air conditioning system. Maybe you can elaborate that a bit more for the audience.
Sure,
I think it's a very important point for our hot and humid climate.
Sure. So the intention is not to have the 24 and the 27 with ceiling fan in the same building or the same space. It was a study that was comparing what happens when you have a building that's at 24 degrees, another one with 27 and ceiling fan. So if you want to provide the flexibility of 24 in one situation, maybe sometime of the year, and then later on we go to 27, that is also possible. But the way I would put forward is our thinking now is maybe we should really go for warmer temperature in the space, not the other way around, because it makes a lot of logic, and from an energy perspective, it's much more beneficial to go for warmer temperature, because thermal comfort is not just temperature. We have been always under this myth that we need to lower the temperature to get comfort, which is not the reality. Thermal comfort has so many parameters, one of which is the air movement. So if we can compensate for that lack of low temperature by having the temperature raised and enhancing with air movement, that's a much more energy efficient strategy. And that's really what I want to get across. So I would not advocate both in the same building, one chooses one way, another one chooses another way. It's probably going to be a little bit difficult to control the building system from that perspective as well. I hope that clarifies that part.
Absolutely. And, as we all know, tropically acclimatized occupants tend to have accommodate at a higher ambient conditions, and you can get the energy benefit from the comfort point of view by maintaining what we are mentioning.
Absolutely. I can share with you anecdotal experience. I have several colleagues and friends who come from Europe. When I receive them and get into my car, and then I put my air conditioning very, very high, airspeed, and then they say, "Oh, can you reduce the airflow? It's too strong for me." So temperate climate people don't quite like very high airspeed generally. And that also I can relate to it, because in the winter conditions in Europe and the cold climate, so to speak, the perception of any air movement in winter is seen as draft. And I can relate to that. But then I think, as you rightly pointed out, Yash, in the tropical context, tropically acclimatized people, we like air movement. We like, fan to just blow at us. We just love it. And then that's at a warmer temperature. Why not bring that thinking, bring that perception, bring that, I would say, philosophy, if you like, into our HVAC system design. And there's so much energy that can be saved doing it that way.
Thank you, Dr. Chandrasekhar. I'll go to the next question for Dr. Olama. So Dr. Ala, the question, I think again you have answered, but I would like everybody to know this. The answer to this question is that, will deep sea water cooling affect marine ecosystem? And is there any is there such an assessment? Maybe you can elaborate on the same for all the audience.
Thanks very much, Dr. Shas. Of course, the temperature of the water that is returning back to the sea is higher than the temperature of the water that you have taken from the sea. So it's very important to pump back the water at levels where the temperature of the sea at that particular region is the same as the temperature of the water coming back to the sea. Otherwise, this may affect marine life. The other thing is the speed of the water coming back. There are certain speeds that should be measured at which you should return the water back to the sea. So those are two very important points, and the environmental study that has to be done before the system is actually enacted have to go through this point one after the other, and it takes about 6 months to do that. But it is very important, the filtration system, the speed of the water, the temperature of water going back to the sea. Otherwise, you will affect the plankton life in this area and reduce the main nutrients of marine life, and this should not be done.
Thank you, Dr. Ala. This is very helpful. Again, there are lots of good questions we have, but in the limit of time, I'll just limit to one question per speaker. My next question is for Mr. Subramaniam. So, Mr. Subramaniam, there's a question in terms of what would be an expected benefit if you go for the chiller sequencing methods and using different approaches of controlling and managing the chillers. I know that's a very, very vague question, but maybe you can shed a little bit of light on in terms of what's an expected range of savings to help the audience and in terms of the benefits that we can get in the water side.
Yeah, thank you. I think we can definitely get approximately 10 to 15% energy saving on that chiller sequencing. Proper sequencing method, because when we do that, we generally go back to the secondary pumping in case it is a primary secondary, or as Mr. Joe said, in case of a variable primary, again there are a lot of things which possibly needs to be fine-tuned on the set points and all those values. And chiller sequencing, yes, the location of temperature sensors are very important. The decoupler line sizing is important. How the balancing is done is very important. So once we, handle each one of these parameters and fine tune them, and I'm sure that we can get definitely a benefit of 10 to 15% on the energy from the chiller plant.
Thank you. That was very, very helpful. So we have a lot of potential that, Dr. Zhao mentioned achieving minimum 20% of the savings. You're talking about 15% of the potential 10 to 15% from the good chiller management. So there is a lot of potential or low-hanging fruits that I can see from the presentation today that the audience here can utilize in their building. So thank you again to all the speakers. We are running towards the end of the session, so I want to thank all the speakers for taking their time out of their busy schedule for the webinar, and it was very, very informative. I really enjoyed the sessions today. I would also like to share a couple of housekeeping arrangements before I end the webinar. So this was a webinar where we had talked about energy efficient centralized air conditioning system. Last week, as Jin Miao mentioned, we have talked about a webinar on disease resilience and indoor air quality. We have 3 more webinars lined up. Next, we have a webinar 3 on smart centralized air conditioning systems, talking about control systems and how it can be used. We have some excellent speakers lined up for the next webinar. We have the webinar 4 on 22nd September on the same time on innovation challenge that was driven by ADB, and then where we have some excellent applications. So some of the novel innovative technologies we have encountered as part of the innovation challenge we would like to share with all of you. With real world examples where people were trying to implement that. And the final webinar on 29th September is on refrigerant management, because climate impacts of refrigerant, how can we minimize that? So I would request all the participants to block your dates and time on your calendar for the webinars for the series. Thank you again for joining, to all the participants, especially for the speakers. With that, I end today's webinar. Thank you very much.
Thank you, Yash. Thanks for inviting. It really was a great session. I enjoyed it too.
Very
Thank
much.
you.
Thank
Dr.
you.
Ala. Thank you, Professor Chandra. Thank you,
Thank you.
Subramaniam.
Thank you. Thank you, Yash. Thank you, Joe, and thank you, Z.
Thank you all.
Thank you, everybody.
Thank
Thank
you.
you. Thank you. Thank you. Thank
Very
you.
excellent
Thank you,
presentation.
Jimmy.
Yeah. Thank you very much.
Thank you, Dr. Zhao. I'm turning off.
Thank you, Yash.
Jimmy on. I'm
Yeah, okay.
closing the session now.